Yeah, good morning, everybody. Good morning. Yeah, how are you? Please, I want everybody to sit right and listen to me. Okay. So, we want to discuss about the work done by its energy. Are we together? Hello. Are we together? Okay, that's good. So, if you are just joining the class, please, I want you to coordinate yourself properly. Okay. Now, you if you were in the previous lesson, we've discussed about it as a form of energy. Can you raise up your hand? Please raise up your hand. Nobody. Okay. Can we have your calculative in physics? You are not with it. We need to solve as many problems. So many. Okay. So now please be seated. Okay. Now let's start. Energy is defined as the capacity to do work or the tendency to do work. Now, there are different forms of energy, and these different forms explains how energy can be used to do work. For example, we have what we call electrical energy. True or false? Now, which means that electrical energy is the energy used in form of electricity to do work. Is that not so? So now if you are going to explain that, we will say that the quantity of heat that is done by material using electricity will be the current multiplied by the what? By the time. True or false? Now which means that this is the work done by the material. For example, if you are using your electrical heater, if you plug it, by the time you put it inside water for some minutes, that's why time is involved. You are going to discover that what? Heat must have been what? Must have been transferred from the what? From the heater to the what? To the water. Is that also? So now which means that the electrical energy is converted to what? To the heat energy. So which means energy can be in different form. But today, we want to look at it as what? As a form of energy. Are we together? Now, let's take it from this aspect. In chemistry, are we together? In chemistry, we must have discussed about enthalpy. Enthalpy simply means heat contents. Are we together? It simply means what? Heat content. That means the total amount of energy in form of heat which a particular matter has to do what? To do work. Are we together? Now let's quickly look at this. Look at the board, please, everybody. For instance, if I have A plus B, are we together? To give C plus D. This particular reaction needs heat for it to what? For it to occur. You know, we have different type of reactions in chemistry. Do you understand? We have what we call thermal reaction. Abi, is that not so? So now let's say this is an example of what? Of a thermal reaction. Now, during this process, there are two things that can be involved. Either heat is lost to the surrounding, do you understand? Or heat is what? Is gained. Are you getting that now? So now if this reaction progress, do you understand? And we have a negative sign like this. This indicates that the reaction is what is exothermic. That it is what is lost to the surrounding. All together. Now the plus sign indicates that it is what is absorbed, which means that there must be absorption of heat energy for that reaction to do what? To occur. All together. Now the total amount of energy that is either given out or that is absorbed is what we refer to as the what? The heat content, which is the enthalpy. That's why if you want to get the amount of enthalpy involved, you are going to say that the change in the amount of heat should be the difference between that of the product and that of the what? Of the reactant of that reaction. Is that not so? Are we together? Now, which indicates that for every reaction, there must be total amount of what? Of heat that must be involved. That is why we have the heat of combustion, heat of solution, heat of neutralization, formation, and co. Are you getting that now? Which means that for every of this reaction, there must be total amount of heat energy that must be involved. So, but here, we want to look at the capacity of heat. The capacity of heat means that the quantity of heat that must be supplied for a particular reaction to do what? To occur. Now, when this heat is being supplied, it ensures that 1 gram or 1 kilogram of water is being raised per Kelvin. Are we getting what I'm saying? Now, this is just very, very simple and it is practicable. The only way we can practicalize this is by using what we call calorimeter. Calorimeter is a device that can be used to measure the total amount of heat energy. Are we together? Are you getting what I'm saying? That is why whenever you are talking about the capacity of heat being specific, you have to measure that heat that is being specific by using what? By using the calorimeter. And that is what we want to talk about. Are you getting the introduction? So now, number one, heat is what? It's a form of energy. Are you getting that now? Now, which means the only thing it deals with the change in the form or structure of a substance. Why is it that a railway can expand? Because it has absorbed heat. Are you getting that now? Why is it that your zinc can expand and later in the day when the sun is coming down, what do you observe? You are going to observe a cracking sound. That is when it is contrasting back. I get to what I'm trying to say. So now which means that practicable heat is a form of energy. Is that message clear to you? Is that clear to you? So now what have I said? I told you that heat is a form of energy. It changes the structure or form in which a particular matter appears. Are you getting what I'm saying? For example, if you take this marker, you put it inside fire, what will happen? It will change. The form will change. It will start changing form. I get what I'm saying. So now, which means that heat is what? Is a form of energy. Are you getting what I'm saying? Is it clear to you? So now, with that idea, you have to listen to this. And I believe you should get this. What I want to show you now. Are we together? Now let's write heat capacity. Let's start with that. All right. Heat capacity. It is the quantity of heat. Heat capacity. It is the quantity of heat. It is the quantity of heat needed to raise the temperature. Needed to raise the temperature. Needed to raise the temperature of a substance. of a substance are we there?
Yes, sir.
By 1 degree. By 1 degree. Now, everybody, can we take it together? 1, 2, 3, everybody. Please be audible. What is heat capacity, everybody?
Heat capacity is the quantity of heat needed to raise the temperature of a substance.
Do you understand? Now, listen. Let me interpret that definition. Hello? Let me interpret the definition. Please look at the board. Heat capacity. Capacity of heat. Are we together? Capacity of heat. Heat capacity. Hello, look at the board, please, everybody. Heat capacity. Heat capacity. Heat capacity. Now, hello, listen. Look at the board, everybody. This is the heat capacity. This is the heat capacity. This thing means work that is being done by the heat energy. I get what I'm saying? Yes. Now, look at the board. Now, the material that you are passing the heat through has a mass. I don't maybe understand what I'm saying. It has what? Mass. So that let's say this is the mass of the material. Are we there? Now, multiply it by the specific. That's the total amount, the total amount of heat energy that matter has. Are you getting that now? Which is represented with the symbol of C. Are we there? Then multiply by the degree rise in temperature. That's from 0 to the highest. Are you getting what I'm saying? So now we can't say that this is the what is the change in what temperature. You can use letter T to represent change in temperature. So now which means that the total amount of heat energy that is passing through that material is equal the mass multiplied by the specific heat capacity, then multiplied by the what? By the change in what? In temperature. Do you understand? Now, why do we define it like this? Let's see. What is work? What is energy? What is energy? Energy is the tendency of doing work, Abi. Now let's see. How do we calculate energy or work done? Yeah, that would be what? First times what? First times what? First times perpendicular distance. You are going to relate it to see the reason they are defining it like that. Too. Everybody look at the board. See. What is force? Mass times what? Abi now? Times what? Everybody just relate it to. Do we have mass here? Do you have acceleration here? Shebi this is acceleration now. Shebi this is specific heat capacity, Abi. This specific heat capacity is like the driving force energy, like acceleration. I get what I'm saying. Do we have distance here? Do you have distance here? Yes, now this is distance now. So now which means as you are eating, let's say this is the body, the temperature will be rising from here to this point. It's the same thing as measuring this in meter, and this one is in degrees Celsius. That's the reason. Is it clear to you? So no definition, no formula in physics that is accidental. There are reasons behind it. Is it clear to you? You don't understand? You don't understand? Let's say this is the heat that you are supplying, HEAT. Sure, you know that this one will be rising from 0 now. Abi, let's say this is from 0 degree. Abi, is that also? Yes. It's just like when you say this is from 0 meter. Sure, you get. And this thing now rise from 0 meter. Let's say this thing stop at 50 degree. So let's say this one is 50 meter. Sure, you get. It's just like the way you are measuring the distance. It's the same thing like you are measuring the degree. So you are comparing degree rise with length. That is why it is expressed as this. That's why you have the mass multiplied by the what? Specific heat capacity. This specific heat capacity is like the acceleration. Are you getting it now? It's just like the acceleration. You know the meaning of acceleration now? That when a body is in motion, and the velocity is what? Is kept constant. No matter how small the time is what? Maybe. That means if it is maintaining equal and constant velocity at equal time interval, no matter how small it is. So the same thing is how you are comparing this specific capacity with what? With acceleration. This distance you are comparing it with what? Temperature. That's why the formula is like that. It's not accidental. Do you understand? Do you understand? So you now write in your note. Right. That therefore, the heat capacity is expressed as Q equal MC T2 minus what? T1, which is differences in what? Temperature. Are you getting that now? Where this represents the quantity of heat that is passing through the body. Are you getting that now? Which represent the heat capacity. Capacity is just the content. For example, let me give an example. When you go to the market, you will tell them that you want 2 kilo, 3 kilo. Abi, is it turkey or whatever? I don't go to the market, so I don't know. So you know, when you get there, they are going to measure the what? The chicken, Abi. Is that not so? So now, the chicken weighs its contents. Is that not the truth? The weight of the chicken is the what? Is what you see when they weigh it. But though there can be evaluation error, there can be measurement error, because such measurement cannot be accurate. No measurement is accurate. Even if you give a tailor to help you sew something, the cloth can never be accurate. But at some point, there can just be a reflection of what? Of perfection. But it cannot be totally perfect. That's why we are humans. Only God is perfect. Do you understand what I'm saying? Is it clear to you? So now this is what you should get. So if you are reading your textbook, if you don't understand, this is what they mean. Very simple and straightforward. Do you understand? Can we progress? Now let's write. Let's write. Specific heat capacity on the line. This is JAMB class. Are we there? There are some things we'll just be eating on the head. You understand? We do not have time to waste. We are right. This is the quantity of heat required. 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 This is the quantity of heat required to raise the temperature of a unit mass. To raise the temperature of a unit mass of a substance. Of a substance by 1 Celsius degree. By 1 Celsius degree. By 1 Celsius degree, or by 1 Kelvin. Please, hello, for exam purpose, those of you writing works, see, I will advise you, listen to me. I will advise you, always take, whenever you want to define this in WAEC, do you understand? Take the standard. Take Kelvin. Don't take degree. I'm not saying that degree is wrong. Oh. I'm not saying that if you write degree says they will fail you totally. No. But you see, in physics, we always respect those that respect physics. You understand what I'm saying? Use the standard for us. When you say STP, you say standard temperature and pressure. The temperature we are talking about is in Kelvin. That's standard. I don't know, maybe you understand what I'm saying. So if you are defining, you tell us that a kilogram in Kelvin. So if you are saying the unit mass, you want to indicate, tell us that it's in kilogram. And tell us that it's in what? Kelvin. But don't put degree. Oh. Don't write degree Kelvin. Oh. It is only the Fahrenheit and the Celsius or centigrade that has degree. Avoid the use of degree with Kelvin. That's not right. Is that taken? Do you understand? So now, in summary, now let's see. So, you should now understand this. Work that has been done work that has been done by a material. You now write Q, quantity of heat supply. Write it that way. Quantity, of heat supplied. Quantity of heat supplied, are we there? Should be equal mass multiplied by specific capacity multiplied by change in temperature. Agree or disagree? Therefore, the heat capacity H will now be mass multiplied by the what? By the specific heat capacity, which is what? H is equal to this. Agree or disagree? That's our conclusion. That's our conclusion. Are we okay with that? Are we okay with that? Can we progress? Okay. So now, the next aspect where we always have, where some students used to have issue is the method of what? Mixture. Are we there? Method of what? So we are moving to that aspect now. We are doing what? So before we get there, let's quickly summarize this. Now let's write. Our heat capacity, which is what? MC, Abi, is measured. Look at the board. It is measured in joule. Okay? Per what? Per Kelvin. Or joule per what? Degree. Are we there? This is how we measure it. Are we there? Now, our specific heat capacity, it is in joule per gram. Do you understand? Per what? Per degree Celsius, or joule per kilogram per Kelvin. Are we there? Or what? Joule per kilogram per what? Kelvin. So now this is the standard unit you must take to measure these things. Is that taken? So if you are solving, remember the units. Are we there? So now let's now move to the method of mixing. That's where we have to obey the law of conservation of what? Of energy. Are we together? Now let's write method of mixture. Okay, now method of mixtures. You write the first one. Are we there? Write heat released by hot body. I'm going to explain everything. Heat released by hot body is equal. Are we there? Heat released by hot body is equal heat absorbed by cold body. Then number two. Are we there? Number two. Heat released by hot body. Heat released by hot body is equal. Heat absorbed by cold body. Case number two is this now. I said heat released by what? Hot body, Abi, is equal heat absorbed by what? By cold body plus the heat plus the heat absorbed by calorimeter. By calorimeter. By what? Calorimeter. Now, look at the board, everybody. As UTME students, there are some things you need to know. And that's what I want to show you. I'm begging the name of God to listen. Method of mixing a substance, method of mixture, there are two cases. There are what? two cases. Now, let me tell you what we mean by the method of mixture. There are times you may have a container like this. Look at the board, please. Look at the board, please. Let's say you have a container like this. Are we there? You now take a rope. You now suspend, let's say this guy is copper. Share you get. And let's say this guy is hot water. Are we there? You now take something like this. Let's say this is stirrer. Are we there? You are now using the stirrer to, instead of shaking it like this, you understand? You are now using the stirrer to mix the water. You know the copper is cold. So now which means, listen, see what's going on now. Let's say that this temperature theta is the normal constant temperature of the copper. Am I communicating? Let's say temperature theta is the temperature of the hot water. That's the water that is hot. Sure you get? No, now which means that if the water is at 50 degrees before, sure you get? Let's say this is mass of water. Sure you get? Let's say this is the quantity of amount of heat that is used, like the specific heat capacity. I get that now. So now which means that this water H, as it is hot, it will drop. The temperature will fall down. Somebody gets what I'm saying? Temperature will do what? Will fall down. It will fall as you are removing the temperature of the copper from the hot water. Share you get? See what is going on here. This is the copper that you are putting there. I don't even understand what I'm saying. So now, this is the temperature of the hot water. That's omigbono, the hot water. This is the copper. Let's say the hot water is, it's the one losing temperature now. So over time, from 50, it must drop. That's the idea. It must drop now. So now when it is dropping, the other body, which is, let's say this is the mass of the copper. Share you get? So now with the mass of the copper plus the specific heat capacity, so which means that the copper itself should increase in temperature. Share you get? And therefore removing the final temperature. Let's say this is final temperature from the temperature which the copper has gotten to rise with. Hey, see, is this thing difficult? This thing is just CS. What did I say? Common sense. I maybe understand what I'm saying. It's very simple. It is simple, practical. Some people are not getting what I'm saying. This one, something that is hot water. Share gets. The hot water is losing its own temperature. The other guy is the one gaining the temperature. So now, from here, you remove the temperature it is gaining. And this one will increase in its own temperature. And this one will now be the temperature of the final mixture. So now it means that if I'm to get this final mixture that is increasing, share you get from here, I can therefore reverse this case and say my mass, this open what? Temperature of the what? Of the final mixture, abi now, minus temperature constant of the what? Of the copper. Because the final temperature of the mixture should be what? Should be much more higher. That's why you see that in most cases they will say, oh yeah, go and look for the temperature of the final mixture. You say what? The temperature of what? It will have, this is cold copper now, you are putting inside hot water now. You know, when you are stirring at a point, you understand? When heat is lost, sure you get, this guy will gain temperature. We have a temperature increase from the natural temperature. And at the end of the day, there will be a stable temperature between this guy and this guy. You know why? Because over time, the copper and the hot water will lose the temperature. So they will not have the same temperature. So that's why they will not ask you that what's the temperature of the mixture of the two of them. That's the final temperature. Shey again, they become hot. So when they become hot, their temperature has increased, but later the temperature will escape. This thing is just common. And the reason most of you have challenges with this is because you did not practicalize this in school. You did not do the real practical. But you must have done the practical now several times at home. When you take your cup of tea, you understand what I'm saying, and you continue shaking it like this, or you are pouring it like this. How many of you have done that? When you take the cup and you are pouring the tea from one place to another, as the tea is passing from one cup to another cup, the tea will be doing what? Losing it to the what? It's very straightforward. Who does not understand? Well, who does not understand? So now it means that in a case of calorimeter, it has a lagging. A lagging. Look at it. It has something like this. That's an insulator. I get to that now. So that to prevent the heat from what? From escaping. Are we together? Let's say this is zinc. Let's say this is the hot water, and this is your stirrer. As you continue stirring, this guy gain heat. This guy too will also gain heat. Shall you see now? So how many of them are gaining the heat energy? The copper and the what? That's the second case. So now this is what happens when you are mixing two substances together. These are the two cases, nothing more. Is it a big discuss with you? We should talk about eating and cooking, but you as a student, you must understand the interpretation of method of mixture before we move to the what? Before we move to the what? Eating and the what? And the cooling. Are we there? Well, now let's progress. Now I'm going to leave a paragraph, right? Write this. So, I'm going to help you with a simple practical. Is that taken? So we have to draw this diagram, and I have to use this practical as an illustration so that you have a better understanding should you want to solve other problems. Is that taken? Well, I'll leave a paragraph, right? Experiments. Experiments to determine the specific heat capacity of a solid. Experiments to determine the specific heat capacity of what? Of a solid by method of mixtures. By method of what? Mixtures. So class, can we draw? Let's draw. How many of you can draw very well? Oh, that's good. So we are going to draw this diagram. Let's use the apparatus. So now we have a thermometer. We have a tripod stand. So let's draw our container first. So we have our thermometer there. Sorry, man, it's not straight there. But just try and so this is our thermometer. So which solid do we have there? We have a solid. So we have a solid here attached to this. So we have hot water. Please, if you are viewing this, please, I want you to draw. So this is our tripod stand. So we have our Bunsen burner. We are supplying heat. So this is our hose. Okay. So now, so if you are viewing this, so now you write this as the solid with unknown specific heat capacity. We don't know the specific heat capacity of this. Is that again? Label, please. write this as the thermometer. Draw and label that. Write this as the thermometer, which we are going to use to take the temperature gradients. Are we there? Then take this as the solid. We don't know the specific heat capacity of the what? Of the solid. Is that taken? Are you done? So remember, I told you that there are two cases. Like the hot body, the hot body, the hot body is losing heat to the what's it called? To the cooler body, Abi. The second case is the hot body losing the heat to the what? Both the cooler body and the water and the calorimeter. Is that taken? So the next one we are going to draw now is the calorimeter. So now you write this as the what? As the thermometer. You write this as the what? As the specific heat. The solid that we don't know the specific heat capacity. Do you understand? That's why I want to do the experiment. You understand? It's a method of mixture. Do you understand? Then we have a stirrer. Okay. You cannot do what? I believe you understand the topic better now. Eh? Were you not in the class when I go? This is the solid with unknown specific heat capacity. Solid with unknown specific heat capacity. Please, we have to be fast about this. This thing should not take your time. You already know these apparatus. Draw them. You have container here, water. This is the solid. This is thermometer. This is the thermostat. This is the person burner. What else are you looking for? What are you looking at? You are drawing. You are science students. So now the next one. The next one is this. So now the calorimeter. Okay. So now, then we have our thermometer there and also our lagging to close the top so that it will not escape. So this is our thermometer. Let me bring it down. Okay. So we are going to suspend our solid in there. So let's suspend our solid. So now we are going to suspend our solid like this. So we just tie it with this. So this is our thermometer. So this is our calorimeter. This is our calorimeter. Okay. This is the solid with unknown specific heat capacity. Is that the key? So if you are done with the diagram, you have to listen to this. So I'm waiting for you. Are you done? This is the thermometer. So this is the solid. We don't know the specific heat capacity. Do you understand? This is the water, the hot water. Okay. Right, let's quickly take this. Let's be fast. You can leave space for that. Or you are writing your notes. Write the mass of the solid. The mass of the solid. Mass of solid to be equal m1 kg. And don't worry, I'm going to explain the process because we don't have much time. Okay, write the mass of calorimeter plus tera. Mass of calorimeter. Mass of calorimeter plus tera to be equal m2 kg. Okay, so then write the mass of the calorimeter plus tera plus water. Mass of calorimeter plus the tera plus water to be equal m3 kg. Okay, then the other case, we take initial temperature of water and the calorimeter. Initial temperature of water and calorimeter. Initial temperature of water and calorimeter. I will explain everything, don't worry. Initial temperature of the water, Abi, and the calorimeter, Abi now. Abi, initial temperature of calorimeter and that of what? And that of what? Water, or let's say and water should be equal with theta 1, Abi. Okay, so now let's take the second one. The temperature of the mixture. Final temperature of mixture, theta 2. Okay, so temperature of the boiling water, I will explain. I just want you to take the identity. Temperature of the boiling water okay, temperature of the boiling water as 100 degrees Celsius. Then specific heat capacity of the solid. Specific heat capacity of the solid. Is equal C1. Are we there? Then we are going to take which other identity do we have again? Specific heat capacity of the water. Specific heat capacity of the water. That should be 4,200 joule per kilogram, Abi, per Kelvin. Abi, per kilogram per Kelvin. That is the specific capacity of the what of. So now these are the identities we need. Is that taken from the experiments? So we don't need too much of stories, but I'm just going to explain what is actually going on there. Is that taken? So you don't need to start spending time writing. Is that taken? So now, you take this as the mass of the solid M1, mass of calorimeter plus stirrer, that's the stirrer you are using to stir the mixture. Then mass of calorimeter plus stirrer plus water should be M3. Then initial temperature of the calorimeter and the water. Do you understand? So later the water we have to lose it to the what? To the calorimeter, Abi. Then before being absorbed by the what? By the solid inside. And that is what theta 1. Now specific heat capacity of the solid is this. And that of water is what? So I hope you have that already in your notes. I'm waiting for you. So having this identity, with this we are going to use it to explain what is actually going on. So with this, you can solve any problem. I get that now. With this, you can do what? You can solve any problem. Though we have about 3 cases. The other one, electricity. We'll look at that also. Is that taken? But this one used to give students problem. Abi, am I wrong? Most students, when they ask them to calculate the temperature of the final mixture, they will hang up. They get confused. Am I communicating? So now these are the identity. So if you already have this in your note, can I see your hand up? If you already have this in your note, can I see your hand up? And what are you waiting for? You have to be fast. Please, I'm waiting for you. I'm waiting for you. I believe you are done with this. So now let's progress. Well, everybody leave the paragraph right. You know why I'm taking this thing gradually? It's for you to understand what is actually going on there. Are we together?
Yes, sir.
Now everybody leave the paragraph, write this. Before you write it, I want you to tell me the identities I've given you. Yeah, read them out. Number 1. Continue.
Mass of solid. Mass of calorimeter plus stirrer. Mass of calorimeter, stirrer, and water.
I want everybody to say that together. Number 1.
Mass of solid.
Number 2.
Mass of calorimeter plus stirrer.
Number 3.
Mass of calorimeter plus stirrer.
Continue. Continue. Very good. Now, we are leave a paragraph. Right. Right. Heat lost by solid. Okay, before you write that, let's write this. Let's write this before you write that. Write specific heat capacity of the calorimeter should be equal C2. Write it that way. That's the last one. Specific heat capacity of the calorimeter. Write it out, take it as C2. At times we used to find that one too. Is that taken? Now everybody leave a paragraph. Leave a paragraph now. How many have I given you? Count it all together. How many? 9, Abby. Is it 9? Have I given you specific heat capacity of solid?
Yes.
Very good. Now I leave the paragraph now. Right. Heat lost by solid in cooling. Heat lost by solid in cooling. Heat lost by solid in cooling. Are we there? From 100 degrees Celsius. From 100 degrees Celsius. Are we there? To final temperature mixture. To final temperature mixture. To final temperature mixture. Now, class, final temperature mixture from what I've given you represent what? Check it. So, class, see what I want to show you. That's why I gave you those identity. Now, what did I ask us to look for? Yeah, right. Tell me. Final what? Final temperature of what? At what? Read that the statement, that sentence. I will... Final temperature of the what? Where see what I'm going to do, everybody. See what I'm going to do. Theta 2, from what I've given you, represent what? True or false? Abi now? So that will now be mass times specific heat capacity of what? What does C1 represent? Do you understand? Multiply by 100 minus theta what? Now, what does theta 1 represent in your notes? Of what? Now, this one is at what? So now, which means if you remove the initial temperature of the water and the calorimeter before it rises to 100, it will give you what? It will give you this one. I don't even understand what I'm saying. Do you understand the illustration? Like this theta 2 represent the final temperature of the whole mixture. So for you to get it, mass times specific heat capacity of what? Of the solid material, which you don't know. Sure you get? Then multiply by the rise in temperature of the water. This is the boiling point of water now, 100. Minus what? Temperature of the what? Of what? Initial temperature of what? Do you understand? And that is what? 100 minus what? Theta. See, hello, listen to me. You have to relate with this table. You have to do what? You have to relate with this. Some of you don't understand what I'm talking about. You are just looking at me. What I'm saying is this. Listen to me. What I'm saying is that this one is theta 2, which is the final temperature of the whole mixture. I get that now. This theta 1 was the initial temperature of water and the calorimeter. So if you are eating, who will absorb it first? Calorimeter and what? And water. When the water becomes hot, it passes it to what? To the container. Abi now? So now later, the two of them, do you understand? They will have individual temperature. Is that also? Which is the final temperature. That's the initial temperature of the body. Subtracting from the rise in temperature of the water. Can you measure the temperature of the calorimeter? No. What we determine, it is the temperature of water. So as the temperature of the water is increasing, do you understand? The temperature of the calorimeter will also do what? Increase, because it will rise from 0 as water is rising. Is that also? You know, if the water is 1 degree, the water will pass the heat to the calorimeter. That's the idea. If the water rises to 50 degrees, it will pass the heat to the calorimeter. So the more the water becomes hot, the more the calorimeter absorbs heat. Yes, now, and which is what? Rise in in temperature from their initial. Initial temperature means that from 0. It may be 0, it may be anything. Sure, you get what I'm saying? The initial temperature of the water and the calorimeter is theta 1. So for you to get this theta 2, sure you get, like for you to get this theta 2, hello everybody, look at the board. Let's say you are multiplying m times, look at the board please, m times c1 times theta 2. If you cancel these two together, this will give you theta 2 equal 100 minus theta 1. So if you say theta 2 equal 100 minus theta 1, it will give you what? Final temperature of the mixture, of the whole mixture. That's what we are saying. It's not clear to you?
Not clear. Yes.
God will help you. So are we together? Now yeah, leave a paragraph, write the next one. Heat gain by water Heat gain by water. Heat gain by water. Who does not understand? Who does not understand? Let me use, everybody look at the board. I'm going to use a level now to explain to you. Yes, I will break it down. Let me use a level to explain to you. Hello. Maybe most of you don't understand. Don't worry. Let me just explain it to you. Listen. Hello. What does theta 1 represent? What does theta 2 represent? Yeah, look at it. Shebi, what did I ask you to look for there? Final temperature of the what? Shebi, this is what it represents, Abi. Look at it. Hello. Where my ear that answer to you understand now? Listen, look at the board, please. You see this theta 2 is the final temperature, Abi. Should be equal mass multiplied by specific heat capacity, Abi. Is that also? Final temperature. Can you see? Equal 100 degrees. Now this 100 degrees temperature of what? Temperature of what?
Boiling water.
Or boiling water, Abi. What does theta 2 represent? Final temperature of what? Now the expression I gave you earlier, what does it mean? What does it say? Heat lost by what? I want to see. I'm trying to help you so that you will understand. It's not necessary I use this textbook. I will explain it in a technical way that you will understand. I'll write it in my own way that you will understand it. Are you getting that now? Listen. Repeat that sentence again. Heat lost by what? Cooling, Abi? Yes. From what? The next one is what? Heat gain by what? Now listen. What does theta 1 represent? What does theta 1 represent? What does theta 2 represent? What does theta 1 represent? What does theta 2 represent? Where class? The expression. Read out that sentence. Hello, if you don't understand, listen now. Read out the expression again. So now, listen. In cooling, Abi in hot, in getting hot. Cooling means that it is what? Shall you understand? Now you see. Theta 1 represents what? Abi now? Now, what does theta 2 represent? Of the what? Look at it. Let me explain it. Practical. Let me just use practical knowledge for you. Shebi, this is 100, Abi. Let me write it this way. Hot. 100. Abi now? Like, you know, when something is hot, this guy is hot. Abi? Now listen. Is it the solid that becomes cool, or the water is the one that becomes cool? Check your notes. Is that not so? Now, what does theta 1 represent? Of what? Theta 2 represent what? Now, class, final temperature and 100, which one should be higher? Final temperature of the mixture and 100, which one should be higher? 100. Is that not so? Now, if this one is final temperature, which is representing theta 2, do you understand? So let's say the final temperature is 43 degrees. Shall you get? Like from 100, it now falls to 43 degrees. Shall you get? Now, which means that if I remove this 43 from this 100, what will be left, class? 57. You see this 57 is the remaining amount of what? Of heat inside that mixture. Are you getting it now? Some people don't understand. You are not getting what I'm saying.
Yes, sir.
What the water is what? 100 Abi.
Yes.
This one is what? The final temperature Abi. Which is the final temperature theta 2 Abi. So now for us to now get the range temperature, that is the left temperature of the whole mixture, you have to remove this resulting temperature after stirring. After stirring everything, this is the resulting temperature theta 2. That's what they mean. Resulting temperature is theta 2. Sure you get. So when you remove it from the highest, what are you left with? 57. 57 here indicates the resulting temperature of the whole mixture. So instead of writing theta 1, everybody put theta 2. Sure you understand what I'm saying? Are you clear with what I'm saying? Is it clear to you? Instead of writing MC1, open bracket 100 minus theta 1, write theta 2 there. Is it clear to you now? So that it will give you the temperature range. Hello, that boy. Do you understand now? Yes, because that's why you see that at times, most of you, when you read your textbook, you may not understand. That's why I'm explaining in details to you. Are you getting that now? Most of our authors here, the way they write textbooks at times makes students get confused. That's why you read and you read and you read and you read and you read, you don't understand anything. To look as if they are saying nonsense. Are you getting that now? So when you continue to stir, there must be resulting temperature. That's what they're looking for. So the final temperature can be when you remove theta 2 from 100. 100 is the highest. Yes, now listen. Theta 2 is resulting temperature. So they will give you this temperature, or they may not give you. Let me tell you how it works. Let me show you how it works. Listen. Everybody see the way it works. You know that there was a temperature, Abi. Let's say you supply it. Everybody see. Let's say you supply it. Look at the board, please. Let's say there was a temperature. Share again. When you supply this temperature, you minus a particular temperature from this one. Let's say this one is 3. Share again. The highest form of temperature. You now subtract 100 from this. Share again. Then there is a leftover temperature, which is theta 2. That leftover temperature, which is theta 2, you understand, is from where? How do you get it? It's by removing that theta 2 from this 100 that was left here. You don't understand? I will explain it again in another way. All of you must understand by fire by force. Let me tell you what I'm saying. Let's say this is a container, like the one you have seen there. You know that temperature will be rising from 1, 2, 3, 4, 5, Abi. Let's say theta 1 represent initial temperature of what? Water, Abi, and what? And the calorimeter. Is that also? The two of them, they have their own temperature. When you now subject it, they will rise. Which one will rise? Calorimeter or water? Water. Is that also? Let's say the temperature, final temperature of water now gets to 100. Sure you get. Now, for us to now get the temperature that is left, you understand, it has to be this 100 minus theta 2 to get the resulting temperature. That is exactly what's going on. That is what we are saying now. We just write theta 2. We just write theta 2 is equal. It's not necessary you put theta 2. What you are looking for is final temperature. They may say calculate final temperature 100 minus theta 2. That's all. So which one are you now looking for there now? You are looking for. Sure you get. That is if they did not give you in the question. If they ask you to look for theta 2, you subtract this theta 2 from 100. That's all. Is it clear to you now? Theta 2 represents what? Final temperature of the what? 100 minus theta 2 will give you temperature range of the mixture. Theta 2 is the resulting temperature, which is called final temperature of the mixture.
So what you are looking for is the temperature range.
Is theta, no, theta 2. I'm going to solve a problem, you will understand. I will solve a problem, you will understand very well. Leave a paragraph, let's write. Leave a paragraph, write. Heat gain by water. Heat gain by water. Leave a paragraph, right? Heat gain by water. Heat gain by water. Are we there? Now let's look at the total amount of heat that is gained by the water. Look at the board, everybody. Heat gained by what? By the water. See the way we are going to. I think from here, you people should be able to understand what I'm talking about. Now, what is M3? What's M3? Abi now. So if I remove, what is M2? You know, if I remove the mass of the calorimeter and stirrer, it will what from this guy. You know, this M3 is the three of them. Total mass of calorimeter, stirrer, and water. This one is just calorimeter and stirrer, Abi. If I remove this one from this one, it will give me what? Mass of water only. Are you getting what I'm saying? Now, what is the specific heat capacity of water? 4,200. Then multiply by theta 2 minus what? What's theta 2? What's theta 1? Share you get now. So which one is having the final temperature? That's the temperature range between the two of them. Final temperature between the whole content of the mixture. What is theta 1? Of what? Initial temperature of what? Do you understand? So from this thing, if they give you, let's say they give you 3,000 joule. Remember, it is measured in what? Share you get. Now they now give you this guy. You already have the mass of this guy. Then you are now looking for initial temperature of the calorimeter and what? It's going to be theta 1. Final temperature will be what? It's not hard. It's just for you to understand what is going on there. Long. You don't still understand. When I was telling somebody that I wanted to treat this topic, they said, we know it. We know the topic. By the time we get to some areas now, some technical areas, you get confused. Hello, please help us open specific heat capacity. I want to show them something. You see, there's nothing difficult about all these things. Hello, is there anybody here that is still having problem with final temperature, initial temperature? Anybody, please raise up your hand. I will go back to the explanation again. Anybody? Hello? Don't. Yes? Which area? Initial. Hello, stand to your feet, please. Hello? Stand up. Read out. You don't have the notes? I don't understand. That's not what I'm saying. Read out the no, not the parameter. I said something earlier before I wrote out the formula. The heat that was what? No, not the heat gained by water. How do you mean? Have you done that? Now let me show you. Everybody look at this. Hello. Look at what I want to show you. Hello. Please just let me move it very close to the camera so that they can see it clearly from wherever they are viewing. Look at this. Hello. This is, please, I believe you can see from there. You can move a bit closer to see what I want to show you. See the way the author, see the way this author puts the explanation. Come and see. Now this one, this is the quantity of heat supply from the hot body. This is the heat lost by the hot body. He represented it with what? QH. Can you see? And this QC mean cooler body. So which one is gaining the heat? Cooler. Share you get which one is losing the heat? Is energy conserved here? Yes. Do you understand what I'm saying?
Yes.
Now look at this. The temperature of the hot, hello, this is the temperature of the hot body. Now he said the final temperature of the what, of the equilibrium of both the substance of the mixture is theta. Can you see? Now this one represents the temperature of the what, of the cooler substance. That's temperature of the cooler substance is equal theta minus temperature of the what, of the cooler body. Temperature of the hot body is this theta h here you see here. The theta h you see here, we can use to represent 100. Are you getting what I'm saying? The theta, are we together? The theta here, are we together? Will you stop this and listen to what I'm showing you? I can see what I'm doing from here. The camera is not your business. This is your business. Now, theta, this theta C here represents the temperature of the cool body. This one represents temperature of the what? Of the hot body. If you look at it from here, see, this theta H here minus theta here, that theta there is the final temperature of the mixture. That you can say they don't write anything under it. Please, at this point, if you don't understand, please, I feel something is wrong. Because I'm sweating. You don't still understand what I'm talking about. Please, if you don't understand, raise up your hand. You don't still understand. Have you written this one? Do you have this one already in your notes?
Yes.
Hello. What I'm explaining is, please, will you listen to me? What I'm explaining to you is this: conservation of energy. Heat that is being lost by the hot body is gained by the what? By the cooler body. Now, the author there, let me use what the author wrote there so that maybe you understand better. Let this one be, hello, let this one be quantity of heat that is supplied from the outer body. Are we together? Let this one be quantity of heat that is absorbed by the what? By the cooler body. So if this is happening, see what will happen here. This guy here is going to be, hello, look at the board now, stop this. This guy is going to be temperature of the hot body. Are we there? Minus, hello, minus, this guy is the final temperature. That's the mixture. I don't maybe understand what I'm talking about. Are you getting what I'm saying?
Yes.
This guy is the final, that's the, this one represents theta 2. This guy is like 100 degrees. Sure, you get what I'm saying?
Yes.
Now this one will not be the, this is the final, do you understand? Minus temperature from the what? The cooler body. Because this cooler body is going to rise its temperature. Sure, you get, now between these two guys, there are temperature range. This one is the one losing the heat to the natural body. So these two ones, they are the stable equilibrium temperature, final temperature of the mixture. Are you getting what I'm saying? Olonro.
The theta means 100.
No. Theta here is like final temperature theta 2.
Okay. Okay.
Hello. Hello, please. Bring this. Everybody write this down. But leave a paragraph for that. Let me solve a problem for you. If I solve one problem now, you understand better. I think so. Well, I leave a paragraph right. Are we there? Calculate the final. Calculate the final or equilibrium temperature. Calculate the final or equilibrium temperature. Calculate the final or equilibrium temperature. Are we there? Of the mixture of 250 gram. Of the mixture of 250 gram of water. At 65 degrees Celsius. Are we there? Is added to 150 gram of colder water. 150 gram of colder water. That's water that is very, very cold. Do you understand? At 5 degrees Celsius. At 5 degrees Celsius. Now listen to what he said though. Neglect heat absorbed by the surrounding. Neglect heat absorbed by the surrounding. Neglect heat what? Absorbed by the what? By the surrounding. Are we there? Take specific heat capacity of water. Shebi you know it now. 4,200. Please, everything. Maybe if I solve this one now, you will understand. Can I rub this guy off? Now let me rub it up. See the way I'm going to solve it so that you will understand. See. Look at the board. Look at the board. Look at the board, please. See. What is the principle? Conservation of energy. Heat from the hot body. Abi? Heat absorbed by the cooler body. Is that not so? This guy represents quantity of heat that is absorbed by the cold body. This one represents quantity of heat that is what? That is lost by the what? By the hot body. Now see what will happen. Everybody look at the board. This is the mass of that hot water. Am I communicating? This guy is the specific capacity of water. Are we getting that now? This guy is the hot water temperature because it will fall. Because it will lose it to the cooler body. Am I communicating?
Yes.
Now this is the final temperature, which is the equilibrium temperature they asked you to look for in that question.
Okay.
Am I communicating?
Okay.
Now which is equal mass of the cold water, that's the cooler water, multiplied by specific heat capacity of what water that is given, then multiply by the temperature of the equilibrium temperature minus the what? Are you getting that now? So now this is the temperature of the cold water. This is the final equilibrium temperature. Now let's put out the identity. Mass of hot water is what? Mass of hot water is what? 200. That will be 0.25. Mass of cold water is what? That will be 0.15 kilogram. Abi now? Specific capacity of water is what? Joe. Abi now?
Yes.
Now, Are we giving temperature of the hot water as what? 65 degrees.
Yes.
Are we giving temperature of the cold water?
Yes.
Then we are looking for this guy. Kiniyo, this thing is not hard. There's nothing difficult about it at all. This thing is just simple experiment, simple practical. This guy is equal to this guy. See, energy is being conceived here. Monitor all these things whenever you are solving. Sure, you understand what I'm saying? So now from here, what are we supposed to get? We have 0.25 multiplied by 4,200 times 65 minus this guy equal what? 0.15 multiplied by this guy multiplied by theta minus what? 5. Abi now? Minus 5. Abi now? So this guy is out. Abi? Now we are left with 0.25 well, let's expand. This guy multiplied by this guy will give us what? 16.25 0. This one 0.15 theta b. This guy times this guy 0.7. We are see. Let's operate. If this guy move here, let this guy come here. Okay. So what are we going to get? We have minus 0.25 theta minus 0.15. This guy minus 0.75 minus 16 points. Yeah, class, what do we have? Minus what? Minus these two. Minus 0. Minus 0. Minus 0.4 abi. 40 theta abi. 0. That's this one and this one is what?
Minus 17.
Minus. Are you sure?
Yes.
So now these two we cancel this abi. Our theta will be what? What's our final temperature? 42. Now class, see yourself. What's the final temperature? This one, is it more than this one? No, now. That's what I'm trying to explain to you. Is this one higher than this one? It's not, it cannot be. It's not possible. That's the final resulting temperature of the whole mixture. That's the English. That's what I've been trying to explain since morning. You don't understand. Look at it yourself. Is this one higher than this one? No. This one is higher than this. Why this one is lesser to this? That's simple matter. That's what I'm saying. I believe you understand. You don't still understand? Yes. What's the question? Why didn't I? No, you don't do that. You don't need to. Nobody will give you. Nobody, except special cases, maybe in A level, whereby maybe we are involving thermal conductivity, where we have the thermal constant and all of that. I don't know why they are always excusing you. I pray that God will help you. Please, Aja, I think I will need that material. I need more series, more questions from there. So we have to solve as many problems. So you give us another question to solve. Eh? You give us another question to solve. So when we are done with what we are doing. So in our next section, we'll be talking about the latent heat, which is the hidden heat. Is that taken? So that may be a little bit complex. One symbol. That's the question. Let me see. A block of aluminium heated. This is the next one we are moving to. This one is electrical by 30 watts, which is the heater. No, this one, keep it. Ensure you don't stop this. We'll be looking for, madam. This is what they are talking about. See, look at it. Hello. See what they are talking about here. They are talking. Sorry for blocking you. They are talking about I square RT equal MC. Share you get. So now in this case now, they are asking us to look for its capacity, which is capital letter C. That's this capital letter C. Capital letter C represents its capacity. Small letter C is specific its capacity. You understand what I'm saying? So now this is the one we are looking for, which is in joule per watt per Kelvin. Shey you get? Abi, all the options, the parameters are given in per Kelvin now. Joule per Kelvin, abi? Are we giving mass there? What are we giving? We are only giving temperature, abi? That's Q, capital letter C, change the temperature and time. That's what we are going to do next. We make sure you give us. I'm waiting for you, please. Are you done? Well, let's progress. Please, I cannot wait. I can't wait again. I can't. No, we don't have time. We don't have time. We have too many things to do. A whole lot. Now, yeah, let's go back to what we were doing before. Now, Have I discussed about lagging effects? Okay, I'll come to that now. All right. Right. Precautions to be taken. That's from the experiment. What are the precautions that we are supposed to take? Precautions to be taken. Number one, the calorimeter should be lagged. The calorimeter should be lagged to prevent heat exchange with the surrounding. The calorimeter should be lagged to prevent heat exchange with the surrounding. Number 2, the hot metal solid. The hot metal solid should be quickly transferred. The hot water solid, hot metal solid should be quickly transferred to the calorimeter. Then lastly, number 3, the mixture should be gently stirred to obtain, should be what? Gently stirred to obtain an even temperature. Please, everybody underline that. That's even temperature. Even temperature. I'll explain it. Some of you may not know what it means. To obtain what? Even temperature. Is that clear? Well, let's now write in summary. Well, write in summary. In summary. In summary. In summary. That's summary. Are we there? Neglecting any heat loss to the surrounding. Neglecting any heat loss to the surrounding. Are we there? Therefore, heat lost by solid. 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 Therefore, heat lost by solid is equal. Is equal. Is equal. Heat gained by water is equal. Heat gained by water is equal. Heat gained by water plus heat gained by calorimeter and stirrer plus heat gained by what? Yes. Now your class, let's write. Let's write. Now everybody look, can we take that together? Heat gained by what? Are we there? Heat gained by what?
Water plus heat gained by calorimeter.
Okay. Now everybody, let's go back to that expression together. Heat gained by what?
Heat lost by solid is equal.
No. Heat gained by water, Abi. Plus what?
Heat gained by calorimeter.
Now, how do we get the mass of water? I want to do, maybe you are following what I'm saying. How do we get the mass of the water? How do we get the mass of the water? Oh my God. How do we get mass of water? M3. Very good. What is the specific heat capacity of water? Thank you, thank you. Now, how do we get the temperature range?
Final temperature minus initial temperature.
Go back to your notes. I gave you this expression. Yeah, theta what? Theta 2 minus theta
2 minus theta 1.
That is why I have problem with some of you. Or you not have problem. I said God will help you. Hello. I will not follow you to the exam hall. You must understand this principle. Everybody go back to the one I gave you earlier. Go back, everybody. Now, go back to the previous notes. Now, the first one I gave you was what? Heat loss by the first thing I gave you before I write down the formula. Yeah, read it out. Heat loss by what? From what? Everybody should talk. You have the notes. We are talk. Heat loss by what? What is the expression? Theta what?
Theta 2 is equal to n times 100 minus theta 1.
Then the second expression I gave is what?
M3 minus M2 1200
Then theta what? What's your theta 2? What's your theta 1? Initial temperature of what? Let's see. All of you must know what you are doing. What's theta 2? What's theta 1? This expression is what? Talk. This expression is what? Heat gain by? If you remove M2 from M3, what do you get? And that should be what? Everybody, let's go back to that. See. I know that most of you don't know that it's not easy. Go back to the previous. Go back there again. Go back. Go back to the values I gave you. M1 is what? M2 is what? M3 is what? This one will give you what? What is M2? Everybody stand up. Everybody stand up. Stand up. Come on, stand up. What's happening? What's going on? Stand up, everybody. What is M3? What's M2? Mass of what? M3 is what? M2 is what? M3 minus M2 will give you what? Who is saying mass of blood water? You need to wake up. You need to do what? You are all adults. I'm not supposed to be. Carry your load. This is how you stand. No, this is how you stand. You have to wake up. Now carry your loads. Well, let's write. Write plus. Let me think. Theta 2 minus theta 1. So that's M1. Now, hello. I'm using the author's indication. I'm using the author's indication. That girl there, what is M1? You. I'm talking to you. Yes, what's M1? Don't do that. M1 is what? Mass of. What's C1? Don't look at your note again. What's C1? What's theta 2? What's M3? I mean you. Everybody, please keep quiet. That girl, what's M1? Don't look at your note again. Please collect her notes. Collect her note from her. What's M1? Eh? C1. C1. Eh? Nobody should talk. She should be the only one doing the talking. This is your life. This is your life. I want everybody to please concentrate. Even if you are, if you are losing this thing, you must ask questions. And those of you that are viewing this from anywhere, please indicate any question you have. We see it from here. Do you understand? If you're having any issue with this, I want you to please be specific. That is why we are using this material to guide, to teach you. Not that we don't know it. I get what I'm saying. So you must be properly guided. If you're having any issue somewhere or you are confused, please ask question. Madam? Hello, madam? You? Yes, you. What is C2? Eh?
Specific its capacity on calorimeter.
Can you say that again?
Specific its capacity on the calorimeter.
What's it at 2?
Okay. Final temperature of the mixture.
Eh?
Final temperature.
What's it at 1?
Initial temperature of the calorimeter.
Okay. So now what does this represent? This expression. What does this expression represent? What does this represent? Eh? This one represents what? Go back to the expression. Heat gained by what plus what? Go back to the expression. Yeah. This expression represents what? This one represents what? This one represents what? What does this say? Lie, don't say final temperature. Stop that. Go back to the English, the expression I gave you. Read it out. Equal. I'm talking about the final expression I gave you before giving you this formula. Heat gain by. Heat gain by. You are. Is equal what? Abby?
Yes.
Let this one represent L. This is just the relationship, and this is the expression. Why now? See, I have said this thing before. JAMB, you have few days to your UTM exam. It's very, very close. If we do not discuss this and if we not get over with this, you know why I'm spending time telling you heat gain by this one, heat gain by this one, heat loss by this one? Because when these people whenever they want to set their own this thing for you, they will not put it in a way you understand. But if you understand the basis, you know how to tackle any problem they give you. Anyone. It is very easy for you to score 300 and above. Very, very easy, I do tell you. Not only by constant practice of the CBT, not only by that. Your hard work is important. And you must develop. must develop interest. There's something I don't want to say. See, let me tell you where the mistake starts from. All together. Where the error comes from is anybody who has refused to develop the spirit of commitment to their leader. Even the Prophet Muhammad said the same thing. Are you getting that now? You must. That is the first steps of wisdom. The first what? The spirit of obedience. The spirit to listen. The spirit of obedience, the spirit to listen. It will direct you. To do what? It will direct you. I pray God will help all of you. I say God will help you.
Amen.
You can sit. Now, in the afternoon, we'll be looking at the latent heats. That's in our next section. Then it means that we are done with that topic. So now let's quickly look at this relationship. Is that the key? Hello? Sorry, please. Hello. Help us open question related to electricity. That's involving specific heat capacity and so before we move to heat capacity calculation. Okay, hello. Okay, for those of you who are joining us just now, okay, I want to quickly show you something related to that's relating the heat capacity and specific heat capacity. Okay, now look at this. Heat capacity can also be indicated with this P capacity with the capital letter C, and that gives mass times specific heat capacity. This is the specific heat capacity, and this is the heat capacity. This is measured in joule per Kelvin. This is measured in either joule per gram per this, or measured joule per kilogram per Kelvin. Okay, so that's for this. So the relationship between this and this is what you see here. So H represents the heat capacity, which is measured in joule per Kelvin. Specific heat capacity is expressed, is with the notation small letter C, and it is measured in either this, that's joule per gram per, or by joule per kilogram per Kelvin. So now this is just the relationship between them. So please note that you can write it down in your notes. You can write it down in your notes. You can write it down. Yes, what's the question? It's not possible. It's not possible. There must be conversion standard. There must be conversion.
In the question.
You must convert it because what we use in physics is kilogram.
What is that unit now accepted?
I don't understand.
No part.
They will give you. They will be specific there. Anytime they give you, they will be specific. But you should always know that physics is Kelvin kilogram standard. In chemistry, we use gram. That's what you should know.
And now, in fact, the children of the rich are not ready to do it because the poor cannot afford it. So the children of the poor are gradually.
What's that?
The question, the temperature is Celsius. How is that answer?
I don't understand.
Unit of the answer.
Because I told you, when we were solving the problem, we did not convert temperature to Kelvin. We converted the gram to what? And remember, I told you, work that is done is energy, Joe. To raise per unit kilogram, I told you earlier. Yes, maybe you have forgotten. I said that in case of WAEC, you remember. I said that. It must be kilogram. And standardly Kelvin does not mean you are converting temperature to Kelvin. But the definition I gave you is obeying this one. Work done. To raise a unit mass by what? 1 degree Celsius. Abi, is that not what you have in your notes? But I said this is the standard. Standard, they leave this standard. That's why physics is physics. That's why what? I was in a biology class and I was talking about social insects. I was talking about the difference between the queen and the workers. I was talking about the features, the abdomens and everything, and the way it is designed, the role of the queen, the role of the workers. Do you understand? The soldiers, you know the soldiers. They are so one of the students said, "Sir, how did they know that this is how they behave?" And if you check biology, there's no how they will know that there's no how one way or the other. Go and check from the series of 1995 across to 2000 and maybe 2 or 2001. They were bringing some questions under that social insects. That's why if you are treating, listen to me, if you are treating biology, there are some topics they have to treat. For example, topics like ecology, ecosystem. Maybe if I have time, I will spend time to take you some of those technical areas. Food pyramid of energy. The law of thermodynamics. Those are the areas. JAMB, that's their interests. That's where they ask student questions. Yes, now. Biological association. God will help you. I said, God will help all of you. I want to solve something related to what. Okay, let's take it from where's this girl? Give us. Do you have any the one that is relating? What is it called? Okay, let's see the one you want to give us. Let me read it out so that everybody from bring it. Okay. Hello. So now we want to quickly take this particular problem from our UTME series, year 2000. Okay, but the number is not indicated there, so you can write a metal of mass 0.5 kg. A metal, yes, a metal of mass 0.5 kg is heated, are we there, to 100 degrees Celsius. Yes, are we there, to a well-lagged calorimeter, calorimeter, of its capacity 80 joule per Kelvin. 80 joule per Kelvin. Are we there? Containing water of its capacity. Containing water of its capacity. 420 joule per Kelvin. 420 joule per Kelvin. Are we there? At 15 degrees Celsius. Are we there? If the final steady temperature of the mixture I'll take it again. And I want you to please pay attention and stop talking. A metal of mass 0.5 kg is heated to 100 degrees Celsius and then transferred to a well-lagged calorimeter of its capacity 80 joule per Kelvin. 80 joule per Kelvin. Containing water of its capacity 420 joule per Kelvin at 15 degrees Celsius. If the final steady temperature of the mixture is 25 degrees, find the specific heat capacity of the metal. Find the specific heat capacity of the what? Class, see the way I'm going to solve this. Please, what time is it? 10:14. I want to have stopped the class now. Hello. Sorry, I was stop the class. Let me quickly solve this. Hello. Let me quickly. Very easy. Specific heat capacity of the hot body, Abi. Abi now? Abi? So that would be mass multiplied by what? By what are you giving there? You are giving the change in temperature, Abi?
Yes.
Times equal what? Times 100 minus what? 25, Abi? That's the steady temperature now. Yes, now steady temperature, that's theta H minus theta now. Equal this guy times this guy, Abi, times, you are giving this guy a C, Abi. What are you giving? 25 minus 15, Abi. So these two guys is out, Abi. So you are using this capital letter C. The first one that you are giving is what? Times, okay, 75, Abi. This guy is what? Times what? Oh yeah, what do you get? 6,000, Abi. You are going to get 6,000. Sorry, wait, oh. We need to get, what's it called? We need to get CO.
Of the metal.
Yes, that of the metal.
Not the water.
Which one are we looking for here? Please read the question out again so that let me represent it properly.
A metal of mass 0.5
A metal of what?
mass 0.5
Okay.
is heated to 100 degrees Celsius
Okay.
and then transferred to a well-lamp tank.
Well, let's see. What is the mass? What is the mass of the metal?
0.5.
0.5. Then the mass of the other one is it given? So let's say 0.5 times what is the heat? Sorry, what is the heat capacity? Is it given there?
Yeah, that's what we are looking for. It's capacity of metal.
This thing. What we want to use? What did they ask us to look for? That is capital letter C equal N. Wait, this is the one we are looking for. This is the one we don't have. Abi? So we are giving mass of metal, Abi. Are we giving the specific capacity? Sorry, the heat capacity of this one of the metal. Are we giving as what?
Is this metal I don't give it?
Go back to the question. Don't confuse my head.
A metal of mass.
Sorry, I'm coming. Somebody should please read the question now.
A metal of mass 0.5 kilogram. We are giving the capacity.
A metal of mass 0.5.
Okay.
The 8 is for the calorimeter, not the metal.
You are the one making mistake. This is what you are supposed to get. We have been giving these guys times this change in temperature. H, Abi, A plus what? Sorry, minus Abi. Then you are giving the mass, the other mass as what? The other mass as what? Were you giving another mass? No. You are not giving another mass. But you are giving this mass. Okay? There is a problem with that question. It's not possible. A metal of mass 0.5 kilogram is heated 100 degrees transferred to calorimeter 80 joule per. Oh, we are given this one now. We are given the heat capacity, which is 420 joule per Kelvin. Is it in the question? Yes. And then what are you looking for again? Nothing now. You are the one confusing me. I've seen what you are looking for. You are the one confusing me. What we are looking for is this. Look at the expression. This is the expression. This guy is equal to this guy. Are we together? Are we, what is the first temperature we are given?
100 degrees Celsius.
For which one? For which one? Eh? For metal, Abi. Oh yeah, look at it here. This is the heat capacity, quantity of heat, Abi. Then multiply the quantity of heat by the change in temperature. What's the change in temperature? 100 minus what? Wait. 100 minus 25. That's where the mistake is. I'm going to re-express it now. Now, you are given 80 joule per Kelvin for which one?
For the calorimeter.
Calo. So now that is 80 joule times what is the change in temperature? Eh? This will be 80 times 75 plus. The second one is what? 420, Abi? Times what? 10. Yes, now this is the heat capacity, the quantity of heat. Do you understand? That is done by transferring the heat from the hot body to the what? To the cooler body. So this one will give us the heat capacity. I get that now. So if you multiply this by this, what will you get?
How many you get for 5? How do you get
80 joule per Kelvin is for what? Calorimeter. What's the temperature?
It contains water at 15 degrees Celsius.
Okay, that's not what I'm saying. So ever bino, move try that to clarify. The 80 joule per Kelvin is heat capacity of what? 420 is heat capacity of what?
Water.
What's the temperature of water given?
15 degrees.
15 degree. What was the initial temperature of water given?
100
degree.
That's the metal. It's the metal that is 100 degrees. Not water.
Okay, the metal is 100 degree. Okay, if the metal is 100 degree, that would be 100 minus 25, Abi. That's 75 here. Abi, this one will give us 75. 75 multiplied by the heat capacity of this. Now, this times this one is what? 6,000. This times this is what? So now let's add it together. What do we get?
10,200.
So our C is what? Please hold on.
136.
136. 136 what? Per Kelvin, Abi. So what will be our C? 136 divided by 0.5 should give us what? That's small letter C. 272. Abi. So which means it is very, very much correct. Well, I'm not even seeing the question, I'm just solving. It's what you are telling me I'm solving with. 80 is for the calorimeter, Abi.
Yes.
This one is for what? Please, somebody should please read the question out to me. No, don't confuse me. You are the one confusing me. What I'm solving is based on the information you are giving me. Somebody should please stand up and read the question out again.
A metal of mass 0.5 kg is heated.
Wait. Ajia, Ejema Binuma, mo fẹ́ sáré clarify kini. A metal of what?
A metal of mass 0.5 kg.
Wait, mass of metal is what? 0.5 kg. At what temperature?
100 degrees.
Who is it, the metal that has the 100 degree or the water?
Metal.
Okay, the metal was at 100. Hold on. The metal was at 100. That's 100 degree. Okay. So, oh yeah.
80 joule per.
That's for the calorimeter, B.
Yes.
That is that the stable temperature? What's the stable temperature in the question? 25. Okay, that's stable temperature 25, Abi. Then what is now that of the cooler one? At what? 15 degrees what? At what? 15 degrees at what? What's before 15 degrees? Let me be fast. 420, Abi. At 15 degree, Abi. That's 15 degrees. Abi now? Is that not so? Oh yeah, let's see. So now it means heat that is lost from the hot body will be gained by the watts. Abi now? Is that not so? So now it means mass of the metal, let's say mass of the metal, Abi, multiplied by the watts. The heat capacity, Abi, multiplied by watts. Temperature range, Abi, that's 100 minus 25, Abi. Is that not so? Now the both of them, that's both the calorimeter and the calorimeter is at a stable temperature of 15 and 25. Is that not so? At this what? At this heat capacity, Abi. The first heat capacity is what? 80 joule per Kelvin, Abi. The second one is what? 420 joule per watt. So that will now be 80. Do you understand? That's the mass M times 80 times 25 minus 15, Abi. Abi now, plus M times 420. Abi now, based on what you are giving me, open brackets, that's times what? 25 minus what? 15. Since they are the same temperature range. So now will not be this, we cancel this all through. Abi now, they are common. M is common. So now will not be C times what? 75. Equal what? 80 times what? 10 plus what? 420 times what? 10. So now that will be 75 capital letter C. 800 plus 4,200 will give me what? What will be my C? This plus the 5,000 divided by 75 will give me what? 66.67 Abi. Joule per what? So what am I looking for? I'm looking for my C Abi. My capital letter C is equal what? So my C will now be what? Capital letter C over M Abi, which is the what? Mass of what? Metal Abi. So that would be small letter C equal what? 66.67 divided by what? 0.5. What do you get? That's what you're supposed to get. So that's the information. So whatever you give me as, if you are reading something out, it's what you tell me. Now I'm going to do. You understand? Now, if you are not being specific with me, you know I'm the one solving. You are the one reading. You are the reader. God bless you. Thank you. Let me pray.
I used to do the same. Hey, please, can you?
Hello, we are live.